All right, guys, let's go ahead and discuss the warm-up so that we can hopefully get through the material today. And then if you have questions about some of the stuff from the other day, maybe we have time for that too. We're going to see how much we can get finished today. You did have an assignment yesterday, 202 acceleration problem set, that I changed the due date to tonight. I did that partway through the day yesterday because initially I had intended to have it due yesterday whenever I was going to be here. But I went ahead and extended it, and I changed it in my Open Math too. So I'm hoping you guys saw that because I changed it in both places. But if not, you can come talk to me if you tried to do the whole thing and didn't know what you were doing. But let's go ahead and go over this first. I'm going to open it up in my Open Math so you can see how it's worded here because it's multiple choice and it's not on my screen. It says examine the position time graph, that should say graph, below, and then answer the questions that follow. Says what direction is the object moving? So whenever you look at a position time graph, and this is the same as it was in the last unit, we can tell the direction of our motion by the direction of the slope, the sign of the slope. If it's a positive slope, we're moving in the positive direction. If it's a negative slope, we're moving in the negative direction. And so looking at this, even though the slope is changing, because it's a curve, even though it's changing, it's always positive here. It's always upward in this graph. And so we would say that the object would be moving forward. Okay, the second question says, which describes its velocity? Again, I just said the slope is changing. You can see that because it goes from a rather flat horizontal slope or shallow slope, and it gets steeper and steeper and steeper. And what does steepness mean on a position time graph? How fast we're going, right? That the slope is the velocity. So if it gets steeper and steeper, that means we're getting faster and faster. So this object is speeding up. Okay, its velocity is also positive. That's the same thing as forward here. Okay, let's see. I think it's just those two. Okay, so let's go ahead and submit. And there we go. Okay, so that's what you should have for the warm-up question for today. Does anybody have a question about the position time graph? We're going to talk more about graphs today, specifically graphs like this that have curves. I think this image is actually from the Gizmo, so I know y'all looked at these types of graphs last week also. But again, we're going to talk about acceleration and graphs, so if you don't already have out your notebook, go ahead and take that out because we are going to take some notes today, and I am going to recommend that you sketch out some of these graphs. I have a couple calculation problems at the end of the notes today so that hopefully we can get to some of that too, because theoretically you learned that yesterday if you watched the video that I left for you, because I left you guys video lectures in my absence of me going through the same stuff last year. So anyway. But we're going to start with just sketching out the shape of an XT, VT, and AT graph for different scenarios. So the first scenario we're going to do is something with zero velocity, something that is not moving. Okay, and so if you have an object that is not moving, then what is your XT graph going to look like? We did this one in the last unit. So if it's not moving, what does it look like? Horizontal. Okay, and it doesn't matter where you put it. Okay, I mean, where you put it is going to be the position that the object's at, but any horizontal line is going to be something that's not moving. Okay, so this would be not moving. I could have drawn it down here. I could have drawn it up here. I could have drawn it below the x-axis if I had space down there. It doesn't matter. If you have a horizontal line, that object is not moving. Okay, on a VT graph, to show that something is not moving, you need to show that its velocity is zero. Okay, the velocity is only zero on the x-axis. So this one has to be drawn on the x-axis to show the velocity is zero, but it will be a horizontal line on the x-axis. Okay, if you draw this one anywhere else, like up here, that's no longer zero velocity, or down here, that's no longer zero velocity, because this graph plots your velocity against your time. The last one, your acceleration time graph. If you have an object that's not moving, that object is not accelerating, so it would also have zero acceleration. Just as a quick reminder, we talked about this in the last unit as well. The slope of your XT graph tells you your velocity. This slope is zero, so my velocity is zero. the slope of my velocity time graph will tell me my acceleration. This slope is also 0, so this has to also be 0. Okay, so you can figure out from the slope something about the next graph. If you want to label this as well, you could say for something with 0 velocity, something that is stationary, it has a velocity of 0 and an acceleration of 0. All right, so that one's pretty easy. So is this one. This should be something that you remember from last unit as well. If I want to show something with the constant velocity moving forward, xt graph, what does it have to look like? Yeah, positive slope. Okay. Now, the line on my graph, does it need to be a straight line? Does it need to be a curve? Does it matter? Straight. Okay, because it's constant. Again, if you have a curve, that means that your speed is changing because the slope is the speed. Okay, so a straight line means that my speed's not changing. It has the same slope everywhere. Therefore, it has the same velocity everywhere, constant velocity. Forward, positive slope. On a VT graph, again, you take the slope of this, it tells you your velocity. This is a positive slope. There are no numbers. I don't know what number it is. It might be positive 2, it might be positive 20, I don't know. Okay, but I do know that whatever this is, it's positive, and so when I plot it on my VT graph, it's going to go up here. And I also know that it shows a velocity that is constant, so I'm going to have a constant velocity of, say, positive 5. It's going to look like that. Okay, again, it has to be above the x-axis this time because this is where you have positive or forward motion. But it does need to be a horizontal line to show that it's not changing. And then again, the slope of this is 0, so my acceleration is 0. Okay, so positive slope means it's a positive velocity. 0 slope here means it's 0 acceleration. If we had numbers on here and this was a slope of positive 5, this would be at positive 5. This slope is 0, so this is at 0. Again, I would sketch these down. Okay, so again, you can jot this down. This is a positive velocity, 0 acceleration. So if you have something moving at a constant velocity forward, its velocity is positive, its acceleration would be 0. All right, Samita. We should jot some of these down. You should probably draw some of the graphs.
Oh, yes.
Okay, just making sure. All right. Constant velocity backward. Again, it's going to be pretty similar, except my slope's going to be negative, but it's still going to be a straight line. Negative slope means negative velocity. So let's say this is a slope of negative 2. Again, there aren't numbers, but let's pretend. And that means that my velocity down here would be at negative 2, okay, if they were numbered. But it would be a constant velocity, horizontal line. So slope here tells me my velocity here. Slope here tells me acceleration is 0, which I know because it's constant velocity. So again, if you have something moving backward at a constant velocity, its velocity is negative, its acceleration would be 0. And y'all have already looked at this in the notes 2 days ago as well. Okay, speeding up, moving forward. So let's add some acceleration in. So far, everything we just talked about was in the last unit. So if you want to show something with a changing speed, and this is what the gizmo showed you in the graphs. If your speed is changing, your slope is going to change. Because the slope of an xt graph, sorry, let me rephrase that. If your speed is changing, the slope on your xt graph is going to change. Because slope on your xt graph is your speed. So if you are getting faster, if you are speeding up, your slope will get steeper. Okay, but you could speed up in either direction. This is specifically talking about going forward. That means the overall slope of this graph needs to be positive, but that it needs to start out more flat and it needs to get more steep as it goes. So it's going to look something like this. Okay, your slope starts out kind of horizontal and then it gets steeper and steeper and steeper in the positive direction. Okay, the slope overall is positive here. It's an upward trend to that curve. So that's how I know it's going forward, and I know it's speeding up because it's getting steeper. If I want to show this same motion on a VT graph, again, all forward motion is above the x-axis. It has to be up here. Has to. Okay, what's the slowest you can go? Or rather not go? 0. Okay, so if you want to show something speeding up, and y'all can write this down, if you want to show something speeding up, and this is true whether it's going forward or backwards, it will always move away from the x-axis on a VT graph because the x-axis is 0. The x-axis is I'm not moving. So if you are speeding up, whether you're going forward or backwards, it will move away from the x-axis. Here I'm going forward, so away from the x-axis up here looks something like this. Again, I don't know what my starting velocity was because I don't have any numbers here, but this one's showing it started out at some kind of already initial velocity. I could have started it at 0. I don't know. But we're just drawing the shape right now. Okay, but again, the velocity is changing. It's getting more and more positive, and that's because this slope is getting more and more positive. The slope of my VT graph is a positive slope. I don't know a number because I don't have a number, but let's say it's positive 3. Then that means my acceleration would be at positive 3, okay, or whatever that number was. But the slope of my VT graph will tell me my acceleration. So if I have an object that is speeding up while moving forward, I have both a positive velocity and a positive acceleration. There's another thing I want you to write down because this is kind of a little tip to help you remember the signs of your velocity and acceleration. If your velocity and your acceleration occur in the same direction, like these are both positive, they're in the same direction, that means you're going to speed up. Okay, so if they're in the same direction, you're going to speed up. You're going to see in a minute that if they're in opposite directions, you will slow down. So if they're both positive, you're getting faster in the positive direction. If they're both negative, we haven't looked at that yet, but if that's true, they're going to get faster in the negative direction. And if they're opposite each other, then you're going to be slowing down, and you'll determine your direction based on your velocity. So we'll look at that in a second. But that's a tip you might want to write down. All right, speeding up in the backward direction. Again, backwards on an xt graph means a negative slope. But if I want to speed up, my slope has to get steeper. So my curve looks like this. Okay, negative slope. It starts out rather flat and gets steeper and steeper, which means I'm getting faster and faster going in the negative direction. Again, if I want to show something speeding up, I have to move away from 0. 0 is my x-axis. But this time I'm going backwards, so it's going to be down here, and it needs to move away from 0. That's speeding up in the negative direction, because I'm going from a velocity of 0 to -2 to -4 to -6. I'm getting faster going backwards. The slope of this line is negative. I don't have numbers, but let's say it's -5. Then I'm going to draw this at -5, or whatever that number might be. But if you are speeding up going backwards, your velocity is negative, your acceleration is negative. Again, they're in the same direction. My signs are both negative, so I'm going to speed up. Same sign. All right, let's look at slowing down. Okay, so I already told you same sign means you're going to speed up. So if I'm negative velocity with negative acceleration gets faster, positive velocity with positive acceleration gets faster. If I'm slowing down, it means they're opposite. They're working against each other. All right, so if I want to slow down while going forward, again, I need a positive slope to show forward motion on an xt graph, but my slope needs to change and it needs to get less steep. It needs to get flatter. That's how I show that I'm slowing down. So it's going to look something like this. That's the basic shape. Okay, again, it might be steeper at the beginning. It doesn't matter, but that's the basic shape, is a curve like that. Okay, on a velocity time graph, if I want to slow down, I need to get closer and closer to 0, because if I get to 0, I stop. Okay, to show that I am forward, I need to be above. It has to be up here. It has to. Okay, that's how I know I'm going forward, and it's going to go towards 0. Okay, in this case, it actually does stop because it reaches 0. Okay, if it reaches the x-axis, you have stopped. The slope of this line is negative, therefore my acceleration will be negative. This is an example of something with a positive velocity, positive because it is up here in the positive region. I know it's changing, but it's forward the whole time, and a negative acceleration. I told you guys if the signs are opposite, you're going to slow down. Okay, so this is an example of slowing down, positive velocity, negative acceleration. This object is moving forward, but slowing down. Last one, slowing down backwards. Okay, again, backwards on an xt graph is going to be a negative slope. Slowing down means that slope needs to start out steep and get less and less steep. It needs to get more and more horizontal, so something like this. On a VT graph, to show that I am slowing down backwards, again, backwards is down here, and anytime I'm slowing down, my graph is going to go towards 0. 0 is the x-axis, so it's going to look like that. This object might have a velocity of -5, and then -4, and then -3, and then -2, and then -1, and then 0, for example. That object would be slowing down while moving backwards because it's going to a velocity of 0. That's where you stop. But the slope of this line is positive. So my acceleration is positive. So if this was a slope of +1, with the example I just gave, it would have been -5, -4, -3. Okay, then this would be at +1, for example. Okay, so again, this is an example of a negative velocity because it's going backward the whole time, but a positive acceleration, those signs are opposite, therefore this object is slowing down. Guys, one of the most common misconceptions people have is they say, oh, if I'm speeding up, I have a positive acceleration. If I'm slowing down, I have a negative acceleration. Not necessarily. This is an example of something slowing down, but it has a positive acceleration. Okay, when you talk about speeding up and slowing down, it's not just the acceleration, but it's also the direction you're going. You have to look at both together. Okay, and again, if those signs are the same, that's when you speed up. If the signs are opposite, that's when you slow down. That is a very common misconception, so jot down whatever you need to help yourself remember that, because I don't want you guys missing it later on a quiz or a test. Any questions about the graphs? I know that's quick, but I would have done this quick anyway. Okay, let's see if we can interpret some graphs. So here I have a position time graph with two different motions represented, one for Ava, one for Rip. And it says differentiate between Ava and Rip's motion. This is from the old unit summary. It's not on the one this time. But if I want to differentiate between their motion, if I look at this, Ava, I have a curve. Rip has a straight line. We just looked at these. Okay, that means that Rip is moving at a constant velocity. Okay, is he going forward or backward? Forward. They're both going forward because both of them have a positive slope. So Rip is moving forward at a constant velocity. What is Ava doing? Speeding up. Her slope gets steeper. Okay, so Rip is moving at a constant speed. Ava is speeding up. They're both going forward. Okay, what happens at 4 seconds where they intersect? On a position time graph, what happens when your lines intersect?
They're together.
Yeah, they're at the same spot. Okay, they're in the same place. They're not going the same speed unless their slope is the same there. Do you guys know how to find a slope of a curve?
Yeah,
You have to of a curve. You have to find like the tangent line at that point. We're not going to do it mathematically, but so don't worry. But the slope, like at this point, if you drew the tangent line, would be like a lot steeper than Rip's. Okay, I can't really show it on here. I just was curious if y'all know how to do that from your math class. But again, Ava passes Rip. She's behind him, and then she's going faster. She passes him at the same place at that time. All right, which person is traveling the fastest at 4 seconds? I just answered that. Ava is going faster because if you look at my red little cursor here, the slope here is steeper. I know it's changing, but if you look at the slope at that point, the tangent line at that point, it is steeper than Rip's slope would be. Okay, which person travels the greatest distance in 4 seconds? Again, your distance on a position time graph, your distances are marked. In 4 seconds, they're at the same spot, and they started at the same spot, so they have traveled the same distance in the first 4 seconds. Okay, at the end of the total graph, after 5 seconds, Ava will have traveled farther because she will be at a position that is farther away from where she started. Questions about any of that so far? All right, at what time do the two people have the same speed? Go ahead and take a look at it. See if you can figure out where you think they might have the same speed. Maybe talk to your neighbor about it. Grayson, what do you think? Where do you think they might have the same speed? Not where they meet. We just talked about that one. That's where they're in the same place. Chase thinks he knows. How do I know how fast they're going on this type of graph?
The slope.
The slope. So where do they look like their slopes are the same?
Like 1 to 2 seconds.
Okay, yeah, somewhere around maybe 2 seconds. But again, this is changing, so it's a little difficult. You may give a different. I gave 2.5 seconds. I said about right here. They look about the same there. But again, you may give a slightly different answer. I'd give you a little bit of leeway on that. Okay, but yeah, they have about the same slope there, about 2.5 seconds. You could say 2. I think this is probably not too soon. They don't look the same here to me, but in this general area right here, they're about the same. All right, which person has the greatest average velocity for the first 4 seconds? Again, I'll give you a second to think about it. Talk to your neighbor. I'll call on somebody. So if you're not sure, make sure you ask a neighbor. Diego. You should probably look at this too. What do you think, Addison? Greatest average velocity. What do you think? For the first 4 seconds. Well, let me ask you this. What is average velocity? How do I find it? We did it in the last test. Do you remember? Yeah, total displacement over total time. So at 4 seconds, who has more displacement? Sorry? I can't hear you at all. You're like whispering. Which one has gone farther at 4 seconds? They're the same. Okay, so if they have the same displacement at the same time, they're going to have the same average velocity for the first 4 seconds. Okay, it's kind of a trick question, so no worries. Okay, they'd be the same there. All right, here is a velocity time graph, different type of graph. I think we actually looked at this in the last unit as well, but it says differentiate between Art and Polly's motion. So this is a VT graph. So Ava, what is Art doing? Speeding up. What about Polly? Constant speed. Okay, so that's the difference between their motion. Polly's moving at a constant speed. Art is speeding up. His velocity is changing. This is a VT graph. Make sure you read the axis. Okay, because otherwise, if y'all think this is a position time graph, you're going to tell me Polly's not moving and Art's moving forward at a constant speed. If you read it wrong, you're going to get it wrong. Okay, but yeah, Art is speeding up because his velocity is getting more and more positive. Polly is at a constant speed. Okay, the slope on your VT graph is acceleration. Okay, so it tells you the change in velocity. All right, at a clock reading of t equals 3 seconds, who is traveling the fastest? So at 3 seconds, who is faster? What do you think, Chase?
3.
At 3 seconds, who's faster? All right, all you have to do is tell me who has a greater velocity. Art's velocity at 3 seconds is 1.5, Polly's is 1. Okay, that, by the way, whenever you look at a single point on a graph like that for a specific velocity at that time, that is called an instantaneous velocity. I think y'all have seen that word before, but in case you weren't sure what it meant, it is the velocity at that instant. Okay, so instantaneous velocity is the velocity at that point in time. And it's really only significant if your velocity is changing, like Art's velocity is changing, so his instantaneous velocities are going to be changing the whole time. Polly's instantaneous velocity is the same the whole time. All right, but Art, his velocity is faster than hers. All right, at 2 seconds, what does an intersection mean on a VT graph? Same speed. Yep, same speed. They're both going 1 meter per second at that time. Okay, if I wanted you to tell me who traveled the farthest at 2 seconds, again, we talked about this in the last unit as well, but you would have to look at the area. The average velocity times the time. That's the equation mathematically for displacement. Okay, and so average velocity of Polly is just 1. Time is 2 seconds. 1 times 2 is 2. Whereas Art's average velocity is only 1/2 because his velocity changed from 0 to 1. And so I end up 1/2 times 1 times 2, which is the area of the triangle. So if you find the areas, you're getting the answer here. Okay, but you're looking at that average velocity, okay, and then that total rectangle. But obviously, you're going to travel, Polly's going to have traveled a greater distance than Art at that point in time. Okay, so here's a just quick question for you. Can an object have 0 speed and still be accelerating? Can you be stationary and accelerate at the same time? No. Cool. We're good with that one. Nope, can't accelerate if you're not moving. What about this one, though? Can an object have a constant speed and still be accelerating?
Yes.
Yes. Okay, because acceleration is a vector. It is a change in velocity. Velocity is a vector. That means that we have to change our vector quantity, which we can do by either changing the numeric value or the direction. You can change the magnitude or the direction. So speeding up, slowing down, or if I turn, I have accelerated. Because I have decreased my velocity in one direction and increased it in another, that's going to be acceleration. So if you turn, okay, you are accelerating. Even if your speed is the same the whole time. If you drive your car in a circle at constant speed, you are accelerating the entire time. Okay, we're going to talk about circular motion at the end of this semester. All right, so this is what was in the notes yesterday for the calculations. Just as a kind of tip, I would recommend that you use the guess method to label all of the information in the question so that you can choose the right equation here, because we have 4 different kinematic equations to choose from. Okay, so your process, the guess method, is going to be label your given and your unknown, then choose the equation that will allow you to solve for that unknown, and then substitute and solve. You can look at the units to help you figure out what type of value you have. Yes, sir?
Do we have to memorize these?
No, you do not have to memorize the equations. They will be given to you. However, you might want them in your notes so that you can do your homework at home. So I would definitely write them down. By the way, this is slide 58. In my notes if you are trying to follow along. All right, so let's try some. Okay, this one says a car with an initial speed of 6.58 meters per second accelerates at a uniform rate of 0.92 meters per second squared for 3.6 seconds. Find its final velocity, find its displacement. So the first thing that you're going to do is you're going to label the information that you're given. You are given an initial velocity of 6.58 meters per second, and you are given an acceleration, and I really should have put signs here. I'm going to say these are positive since I didn't put a negative in front, but I should type the positive and I didn't. But the acceleration is 0.92 meters per second squared, and I'm also given a time of 3.6 seconds. Okay, so they gave us VI, they gave us A, they gave us T, and they want us to find final velocity, and then they want us to find, in the second question, displacement. Okay, so if we have VI, A, and T, look at these equations. This one has VI, A, and T and allows me to find final velocity. I'm going to use equation A to answer the first question. If you label your variables, it's very easy to see that that one's going to be the one that works. Okay, I can use that one to find the answer to the first question, this equation. To find displacement from VI, A, and T, again, look at these equations. Like letter B, I can't use until I find VF. Since I'm going to find VF anyway, I could use that one because it has VF, VI, A, and delta X. Delta X is your displacement. So I do have 2 of those, and I'm about to find one, so I could use B. But if you keep looking, if I wasn't trying to find final velocity first, I could use C, because displacement right here, I have VI, I have T, I have A. Okay, this one down here, again, I couldn't use until I find VF. So most of the time, the equation that you're looking for, there's only one you can use unless you find more information. So the ones that I can use right away would be A and C. I could do it in either order. I could solve for either one first with those 2 equations. But again, you can do whichever one you want. I'm going to go ahead and switch over to my document camera so I can actually work this out and you guys can follow along with me. I've already labeled the information in the question. Okay, so those are the information, pieces of information I was given, and I'm looking for these. Again, when I looked at my list of equations, I said I was going to use this, VF equals VI plus A times T, and I'm going to use that to solve for the first one. Okay, so if I substitute into this equation, I have VF equals, VI is 6.58 plus A is 0.92 and T is 3.6. Guys, the hardest part of this unit is simply picking the right equation. Okay, because once you know which one to use, this part's easy. Plugging it in is not the hard part. You have to get into the habit of looking at it, labeling everything so that you can pick the correct equation. If you can't do that, you're never going to get it right. So you do have to practice this, And you do want to write these out. It's not extra work, I promise. It's so that you can figure out which equation to use. You're looking for VI, A, and T. And you need it to also have VF, otherwise you can't solve for it. So if you label them, you're like, I need the equation that has VI, A, T, and VF. There's only one. So if you do that, you should know, okay, I'm using this. Once you have this, though, let's go ahead and solve. Let's do 0.92 times 3.6. And then add to that 6.58. And we get 9.892. Meters per second. No, you do not have to do sig figs. Unless you just really want to. Didn't think so. Okay. All right, so this is what you would get for final velocity. Okay, now we're going to do delta x. Now because I know VIAT and now I know VF, I have 3 different equations I could use, and it honestly doesn't matter which one you do. Okay, I'm actually going to use the one that I don't need VF for, because if I had wanted to do this one first, I could have. But again, there are 3 equations here, so you pick whichever one you want. This is the one I'm going to use. Delta x equals VIT plus 1/2 AT squared. That's the formula. Okay, again, you have 2 other ones that could work, but this one's already set equal to delta x, so I'm going to go ahead and use it. Substituting in, I have 6.58, that's VI. T is 3.6, 1/2, A is 0.92, and then T squared. By the way, it's only the T that is squared here, not the whole thing. Okay, so just the time, 3.6 squared. So now I'm going to put this in my calculator. I'm going to go ahead and multiply the 6.8 times 3.6, or sorry, 6.58 times 3.6. And I get this, okay, and then I'll do the other part and then I'll add them together. So 1/2 times 0.92 times 3.6 squared, okay, and then I'm going to add that number to that number to get this, 29.6496, which I'm going to round to 29.65.
Could you zoom out a bit?
Sorry?
Could you zoom out a bit?
All right, so that is how you would solve those couple of problems. I have another one on here, and I'll go ahead and put it on the screen in just a second so that you can maybe try to just pick the right equation. Start there. You can't do anything else until you pick the right equation. Sometimes with some of these it might help to even draw a picture, but the main thing that students get tripped up on is simply choosing the correct equation to use, because there are 4 of them and there are so many variables and the equations are all similar. But each of them is missing one variable. Okay, so each of them is only really going to work in one situation unless you happen to have all of the other information and you have multiple options. All right, so here is another one. 2 of them actually. If you want to look at them and try to figure out which equation to use, and you can try to solve it too, but just figuring out which equation to use, okay, that would be a good start. But again, I also want to give you guys some time to work on the MyOpen Math assignment if you did not finish it yet. I know some of you already finished it, but if you did not finish 202, you could open that up if you're feeling okay with the math. If you're not feeling okay with the math, try this first, and I can come around and I can check and make sure you're using the right equation. Okay, I'll go ahead and solve these on my own real quick. That way I can tell you what the answers are, and then you can know if you did it right or not. Okay, so give me a second, I'll do that. And then once you are finished with this, or if you're feeling confident and you don't want to do these 2 and you just want to open up the assignment, you can. But the assignment 202 acceleration problem set is due by 11:59 p.m. tonight. So that is your classwork for the remainder of the period, which since we're on advisory schedule is 10 minutes that you have left. So you have some time in here to try some of it. And then if you're not finished, I know you all hopefully started it yesterday, but if you're not finished, then you can take that home and work on it as homework. Let me move that out of your way. All right, so go ahead and see if you can figure out how to solve them, or at least get the equation right. And if you have questions, let me know.